Welcome to Earth Science Lecture. I'm Professor Diana L. Pomeroy, and this week we'll discuss igneous rocks and volcanoes. Igneous rocks are the first rock type in the rock cycle, which is described by the geologist James Hutton in the 1800s. On this slide, we have an image of the rock cycle. We have all three rocks shown here. We have igneous rocks, sedimentary rocks, and metamorphic rocks. And for this lecture, we're just going to be focusing on igneous rocks. The word igneous comes from a Latin word ignis, which means to ignite or to catch fire. Igneous rocks form from the fires of the earth, from silicate minerals that grow under immense heat and pressure in the magma of Earth's mantle and crust. So recall from previous lectures that the mantle and the crust of the earth, specifically the asthenosphere, contain layers of magma, this molten rock that exists under the Earth's surface. And recall also that it takes immense heat and pressure in order for the rock to develop in that state. So on this slide, we have a picture of an example of an igneous rock that's granite. And we also have a penny for scale. In later lectures, you're going to see a lot of pictures with rocks with different objects used for scale. It's a thing that a lot of geologists do to get a sense of how large particular rocks or objects are. So magma is, again, a form of molten rock. It's rock that's been melted into a near liquid state by immense heat and pressure. Magma is molten rock, and when it rises to the surface, usually from volcanic activity, it will develop into a substance that we call lava. So magma is a substance that's below the Earth's surface and gradually cools and solidifies, and lava is a substance that forms above the Earth's surface due to a volcanic eruption. So magma, because it's at depth in the Earth's crust, it cools much slower than lava does, and as a result, the minerals that crystallize out of magma solution tend to be much larger in size than the crystals that form in lava solution or even volcanic ash. So igneous rocks that develop in this way, they develop larger crystals, are what we refer to as intrusive or plutonic igneous rock. The term plutonic comes from the Greek or Roman god Pluto or Hades, which was the god of the underworld in that mythology. Lava, on the other hand, again, because it cools so quickly, it forms from extrusive processes. Extrusive or volcanic igneous rocks, those result from lava. So that lava that's extruded during a volcanic eruption, including volcanic ash, those substances are what solidify into extrusive igneous rocks. So those rocks tend to have smaller to absent crystals, and they have distinct textures. And so again, there's a distinction between magma and lava as shown on this slide. Molten rock, remember, originates in the uppermost layer of the mantle, typically in the asthenosphere. And recall that this layer is what causes the process of magmatic convection to occur. Magmatic convection is a process where superheated magma rises to the surface at particular points in the Earth's crust and generates new seafloor, what we call a ridge. That material will then spread out on either side of that heat source, and the magma will then sink back down because it's gaining density as it cools. As it gains density, the overlying crust gets dragged along with it back into the asthenosphere and then destroyed at points on Earth that we call a trench. This process of magmatic convection is continuous. It's been going on Earth's surface for billions of years. And it's through this process that we get different types of minerals, silicate minerals, that will solidify out of magma solution at different temperatures and pressures in the mantle and in the crust itself. So recall that the crust of the Earth is not a separate layer that floats on top of the asthenosphere. It's in fact connected to it, so that anytime the magma flows under the surface, it's going to get pulled back down and then destroyed and regenerated in a continuous cycle. This regeneration process is all because of the fact that the interior of the Earth doesn't have the same temperature everywhere. And that's a good thing, because if the interior of the Earth was the same temperature, if it was thousands of degrees Fahrenheit or Celsius like it is at the core, the surface of the Earth would also be thousands of degrees Celsius, and nothing would survive on our surface. So what happens inside the Earth is that the superheated core, the hottest layer inside the Earth, it provides heat to all of the other layers inside, specifically through the lower and upper mantle. Because the mantle layers, this silica rock, is so compressed, there's such immense pressure, those layers are more solid than they are this plastic flowing layer that we have in the asthenosphere. And in fact, there's portions of magma that will become more heated or less heated in the asthenosphere itself. So the animations that we've been seeing in this class so far and the illustrations we've been looking at are very simplistic in comparison to the actual phenomenon of heat and density exchange that occurs in that layer of the uppermost mantle. So this process where we've got superheated core and then the heat radiates to each of the layers, slowly diminishing over time and with decreasing distance, getting closer to the surface. This process is what we call a geothermal gradient. And on average, the Earth's surface temperature is about 25 degrees Celsius, which is, around 75 to maybe 90 degrees Fahrenheit on any given day. Understand that there's any subtle variations in that temperature can cause immense changes, not only in the interior of the Earth, but on its exterior as well. So this process by which we get differences in melt in the magma and the mantle produces different, again, types of minerals that solidify out of that magma solution. So magma molten rock forms as this heat radiates from the core, and at different rates, along with different temperatures and pressures, specific types of silicate minerals are going to form out of that magma solution. So differences in the rate of melt are what we call partial melting. So it's not like going from a solid state of water to a liquid state of water. Those are different phases of matter, by the way. So there's three major phases of matter. There's solids, liquids, and gases. So recall that if you take a solid cube of ice, for example, and if you start to melt it, it will become a liquid. So if you add enough heat to it, it will melt. But the chemistry of that substance does not change. So water, the molecule water, H2O, does not change as it goes from a solid to a liquid state. The only thing that changes is the structure, the way in which those molecules are arranged, but not the molecular chemistry itself. This is different with rocks. If you melt down rocks under immense heat and pressure, what will happen is certain minerals will remain melted at greater depths in the crust and mantle, and other minerals will solidify out of that solution at different rates and pressures. And so because of these differences in melt, we actually get different types of volcanic eruptions and also different types of interactions between the magma that's present, say, in the deeper parts of the crust or towards the surface. So there's different types of partial melting that occur in different locations on the Earth's crust, and we're going to learn about those next. The first type of partial melting occurs along divergent plate boundaries. Now recall from our plate tectonics lecture that with divergent boundaries, the tectonic plates are actually being pushed away from each other. And this is because the superheated magma is rising to the surface in one area continuously. Because of decompression, this magma as it rises to the surface is not really changing its temperature, it's only changing its pressure, because the heat source is constant. So because the heat source is constant, this magma is always hot. And because the magma is always hot, the resulting volcanoes that will form are what we call shield volcanoes. They tend to be larger, and their eruptions are fairly continuous over time. An example of this, again, would be the hotspot volcano that we find in the Hawaiian island chain. So Kilauea is an example of this. With Kilauea, which has been erupting continuously since 1986, that pool of magma is continuously feeding into that one area. And there's, again, no difference in pressure here. Or there's a difference in pressure, but no difference in temperature. So the temperature doesn't differ, only the pressure does. And this process is known as decompression melting. So decompression melting generates shield volcanoes, which again have this continuous eruption style. It's a more gentle eruption style than what we see at other types of boundaries. So again, decompression melting, you're just changing the temperature from a greater temperature underneath the surface to a lesser temperature at the surface, rather than the pressure that's experienced itself. And keep in mind that this temperature differential is not all that great either. We're going from a superheated source to a slightly less heated source, but it's not that great of a difference. And as a result, the chemistry of that magma and lava are not going to be too different from one another. We'll discuss differences in chemistry in magma and lava in the volcano lecture. The other type of partial melting that goes on is what we call flux melting. This happens along convergent boundaries, specifically along what we call subduction zones. So recall that what happens along a subduction zone is that oceanic crust and continental crust converge. Where these crustal plates meet, because oceanic crust is more dense than continental crust, it will get pulled back into the mantle through that process of magmatic convection and destroyed. Oceanic crust has a layer of seawater that's carried along with it. And so this layer of seawater is going to be pulled into the mantle and then destroyed and melted off. And so that seawater is actually going to mix with the magma melt in the asthenosphere. And as a result, there's a subtle change in pressure and temperature within some of those sections of that melted rock. And so they're going to essentially travel slowly up within the crust of the earth and develop a distinctly different magma chamber or pool of magma inside those volcanoes we find bordering that trench on the earth's surface. So that process where we're adding what we call volatiles or chemicals like water or oxygen or carbon dioxide into any kind of reactive material like superheated magma, whenever we do this process is known as flux melting. So again, flux melting has to do with extreme differences in temperature and pressure. And that's again due to the fact that we're adding seawater into the mantle, causing that melt to be very different. The volcanoes that result from this type of reaction are distinctly different, and they're more explosive in their eruption style than what we find at divergent boundaries or even along hotspots with our shield volcanoes. So a totally different type of volcano, a completely different type of chemistry will occur. On this slide, we've got different types of magma that develop, and you'll notice that there's different percentages that are listed here of silica. So recall that our silicate minerals, we have tons of them. Quartz is the most common one. We have several other types of silicate minerals. And in fact, we group these into two major categories according to what we call Bowen's reaction series, which I'll show you about in the next couple slides. The first category is what we call mafic minerals. Mafic refers to magnesium and iron rich. So those minerals, magnesium and iron, tend to be more present in these dark silicates. So the minerals that are considered dark silicates include olivine, pyroxene, amphibole, and biotite mica. These minerals tend to remain at depth in the mantle and in the crust, and they tend to remain in magma solution longer than the other type of silicate, the felsic silicate minerals. Felsic silicate minerals are otherwise known as the light silicates. They're primarily composed of minerals like feldspar and quartz. So feldspar and quartz tend to be grouped in this category of felsic or light silicate minerals. And due to their structure, they tend to have a greater proportion of silica. Because felsic minerals have a greater proportion of silica in their structure, what this means is that there's a distinct difference in how, again, the magma will react and an eruption will take place than what we have with our mafic minerals. So we have felsic minerals and mafic minerals. Also, the felsic minerals crystallize later. They develop closer to the surface. And again, this can cause distinct differences in how these volcanoes can erupt. So we have felsic, mafic minerals. A mixture of felsic and mafic minerals produces an intermediate magma. This is not as common as maybe a felsic or a mafic magma, but they do exist. Intermediate classification means that you have a mixture, about a 50-50 mixture of felsic and mafic minerals in your magma solution. Ultramafic means that you almost have 100% mafic, very iron and magnesium rich content in your minerals that we find in that magma solution. And again, this could cause a total difference in how this reaction and resulting volcanic eruption takes place. So on this slide, we have a diagram that shows changes to the amounts of felsic or mafic minerals present in the magma solution. And in turn, this can produce differences in color and appearance of our igneous rocks. So we've got felsic minerals again, quartz, muscovite mica, and the feldspars. And we have our mafic minerals, which are the dark silicates, like biotite mica, amphibole, pyroxene, and olivine. On this slide, we have Bowen's reaction series. Bowen's reaction series was developed in the early 1900s by Norman Bowen, who was a scientist that took chunks of rock and melted them down in a kiln, or basically a superheated oven. And by melting them down, what crystallized out were different types of volcanic glass. These different types of volcanic glass produce different color variations, and also distinctly different types of minerals would form at different temperatures and pressures of the melts. And so he developed this table that we use called Bowen's reaction series to categorize our different types of igneous rocks based on their mineral content. So at greater temperatures at the top of the graph, we have what's known as high temperature melt. So higher temperature minerals will form here. So often, again, the mafic minerals like olivine and pyroxene, those tend to form at greater temperatures and pressures in the crust. In addition, on the opposite side of the chart here, we've got calcium-rich feldspar. This also will form at greater depths in the crust, but I tend to lump all the feldspars together as felsic to keep things straightforward for this class. We just recognize that technically feldspars are part of this category as well. So again, high temperature and high pressure conditions form minerals like olivine and pyroxene, which will then solidify and combine together to make ultramafic or mafic igneous rocks. So on the right side of this chart, we've got ultramafic and mafic, and these are categories that we use again to define the mineral content that we have in our igneous rocks. Moving down the chart, we've got lower temperatures at the bottom. And so lower temperature minerals that develop lower temperatures and lower pressures, these are the minerals that are last to crystallize in Bowen's reaction series, which include potassium feldspar and then muscovite mica and quartz. These minerals are often what combine together to form felsic and intermediate igneous rock types. So again, we've got intermediate igneous rocks, which are a mixture of, say, biotite mica, amphibole, and then our potassium feldspar, and our felsic minerals like potassium feldspar and quartz that would combine together to make other types of our igneous rocks. So this chart again just tells us how different temperatures and pressures produce different types of minerals that solidify out of partial melts, and that these will then crystallize into distinct types of igneous rocks. So remember that we've got two major ways in which igneous rocks can form, which I introduced to you at the beginning with our magma and our lava. So with magma, these plutonic igneous rocks, these intrusive igneous rocks, they have a distinctly different appearance than our extrusive igneous rocks. So our intrusive igneous rocks can form what we call intrusive structures within the Earth's crust and mantle. And the majority of these structures are things that you will probably be learning about in other classes. If you go on in physical geology, or let's say you're taking the lab component for this class, you may have to understand the differences between some of these terms. But for our class, what I want you to focus on is one term that I've circled here, which is called batholith. A batholith is an immense pool of magma that gradually cools and crystallizes. So depending on where this forms in the crust and how it develops, a batholith can solidify very slowly over thousands to millions of years of time. And in turn, this batholith can be uplifted and then eroded. We have examples of this throughout North America, and I'll explain some examples in a few moments of batholiths that have undergone this process, and you can actually walk on these surfaces on Earth today. Then we have our extrusive igneous rocks. So again, these form from lava or volcanic ash. Sometimes these are termed volcanic igneous rocks for that reason. So inside of a volcano, we've got a pool of magma called a magma chamber. And this is what feeds into the volcano and causes the eruption to take place. When a volcanic eruption occurs, the magma chamber will actually expand and the magma inside becomes activated. It will be superheated and constantly moving. And in that process of motion, some of this magma gets fed into fractures or cracks or fissures inside the volcano and actually make their way out to the surface. When magma makes its way to the surface, it develops into lava. Now, lava flows have different rates, different temperatures and pressures depending on their chemistry, which I'll talk about again in more detail with the volcano lecture. But with these lava flows, they solidify into pools of lava that are extrusive. So these extrusive pools, as they solidify, can develop into fast cooling of smaller crystal type extrusive rocks. Then we have volcanic eruptions that produce a lot of volcanic ash, and just like a lava flow, ash flows can also be preserved as extrusive or volcanic igneous rocks. So we can essentially classify our rocks based on two things, and all rocks in the rock cycle are classified in this way. They're classified based on two concepts: texture, or the appearance of a rock, and then the composition, or what the rock is actually made of. Igneous rocks are classified based on both the texture, or the surface appearance of the rock, and the mineral composition, what the rock is made of. So on this slide, I have an image of an iconic monument here in California. This is an image of Half Dome, which is part of a granite monument that we have in Yosemite National Park. Yosemite National Park is part of what we call the Sierra Nevada Complex. It's a series of granite mountains that have been uplifted and eroded over time. So in fact, the Sierra Nevadas were once part of an immense batholith, a pool of superheated magma that fed into ancient volcanoes over a span of maybe 200 million years. So for hundreds of millions of years, that entire Sierra Nevada range was actually under the Earth's surface and fed into a series of ancient volcanoes on land. That process ended around 25 million years ago. The process of subduction along our ancient coastline had ended, and that volcanic process ended as well. And so the magma chambers gradually cooled and solidified into the granites that we have in the Sierras. And those granites were then further sculpted by the process of glaciation. Glaciers are immense walls of ice that gradually move across the Earth's surface. And during the last ice age, or the last major glacial maximum, those glaciers gradually moved and sculpted, essentially carved out the surface of areas like Yosemite National Park. So during the last ice age, that entire area was sculpted and carved out by that process. Similar phenomena have occurred in different places. Mount Rushmore is also carved out from granite. So those massive, that massive monument was actually gradually carved out over a span of, several decades by people. But that process, again, is very similar to what happened with the carving, the natural carving that we see here of Half Dome from thousands of years ago. So oftentimes, even like your granite countertops, anytime that you have like granite in construction, in walls and floors, things like that, that substance, those rocks are made of distinct mineral components, and they have different appearances based on the size of those mineral crystals that have been developed in that magma melt. So texture is based on an igneous rock's size, shape, and arrangement or sorting of its mineral crystals. In terms of intrusive versus extrusive textures, remember that with intrusive igneous textures, we've got igneous rocks that form more slowly than what we have with extrusive textures. So as they form more slowly, you get larger crystals that form out of that magma solution. So here on the slide, we've got 3 examples of a crystalline texture that can form in our igneous rocks. And really it's the latter two, the phaneritic and porphyritic textures, that we're concerned with here with our intrusive igneous rocks. So both these examples are types of granite. So the first one here is phaneritic. In this case, all of the crystals, we have crystals of biotite, which are the black mineral crystals here, potassium feldspar, which are the pink crystals, and we've got some muscovite mica embedded as well as maybe some feldspar. All of these, okay, and some quartz, all of these minerals are roughly the same size and shape. They are visible with the naked eye, either just by looking at a sample or even looking, if you were to walk up to sections of, say, Yosemite National Park, walk up to the monuments and look very carefully, you would see that the minerals themselves are still embedded in that rock. And they're all considered what we call phaneritic, so they're all roughly the same size and shape in their crystalline structure. Porphyritic granite is a little bit different. There's sections of feldspar in this sample that have become increasingly larger than the other pieces that are embedded here. And so this process is because this particular section of granite was remelted or reheated. And so that allowed for some of those crystals to grow much larger than what we have in the background. So porphyritic igneous rocks, that porphyritic crystalline texture is characterized by some larger crystals embedded within smaller crystals, yet all the crystals are visible to the naked eye. The last category here is actually the first image on this slide. So we've got aphanitic texture. So aphanitic means that there's no crystal grains that are visible, or they're very, very small. So you can only see them with a device that we call a hand lens. A hand lens is, or a jeweler's loupe, is what we use to magnify the surface of a lot of rocks to see their mineral crystals. And so basalt is an extrusive igneous rock that tends to have this kind of crystalline appearance, this crystalline texture. So all 3 of these examples are examples where mineral crystals developed in the igneous rocks. You can see them on the surface. Aphanitic, not so much, but phaneritic and porphyritic, yes. The next texture that we have, the next series of textures that we have, are for extrusive or volcanic igneous rocks. And it's understandable that most often we tend to have a lot more extrusive igneous rocks that are better studied and understood than what we have with our intrusive specimens, because, again, remember that intrusive rocks usually take a very long time to form, thousands to millions of years to gradually cool, and so the crystals in those specimens can take longer to grow and develop, and so we can actually see them. With extrusive igneous rocks of volcanoes, there's more volcanoes near surface, 1. 2, when these volcanoes erupt, it's an instantaneous process. And so in this way, lava and ash, as it forms, can solidify very quickly. So the textures that form here are significantly different than what we previously observed. So the first texture that we have is glassy texture. And this develops when lava flows are instantaneously cooled, usually by touching cooler air like icy air, or when they hit seawater. So surface seawater hits that lava and cools it instantaneously, essentially flash freezing it and developing it into a glass. So the best example of this, of an igneous rock that has this kind of texture, is obsidian, and that's what's pictured here. You may be familiar with obsidian from the series Game of Thrones. Game of Thrones featured a type of obsidian that was referred to as dragon glass in the fiction, but essentially, kind of like the fiction, obsidian has been used in tools and weapons by people for thousands of years. We've used obsidians in arrowheads and for cutting and carving, for weaponry, for a very long time. Obsidian, again, is volcanic glass. And other times it's used for decorative purposes. Obsidian is, even though it appears as if it would be made of mafic minerals, obsidian is actually felsic in its mineral composition. So that's obsidian, glassy texture, volcanic glass. The next texture that we have is what we call vesicular. It comes from vesicle or vesicle vessel, holes. So vesicular textures form when either volcanic lava or ash will cool slow enough to form bubbles on the surface or become aerated. In other words, it's got holes in it. And so for those of you that have trypophobia, which is a fear of holes, I apologize for this next image, but essentially we've got two rocks here with a vesicular texture, and that includes scoria, which is a form of a mafic lava that is fairly frothy and solidifies into this rock. And then we've got pumice. Pumice is actually a volcanic ash that usually forms from ash flows, whether they're pyroclastic flows or not. Pumice solidified from that ash, and it's aerated, so it's super lightweight. You can actually place it in water and it will float. So both of these rocks, scoria and pumice, are examples of igneous rocks that have vesicular texture. Again, they're aerated, so they've got holes in them. They form almost instantaneously, but slow enough to where the bubbles on that surface will gradually pop and develop this aeration that we can actually observe in the specimens themselves. The last type of texture that we have with our igneous rocks is what we call pyroclastic texture. This comes from a pyroclastic flow. Now, pyro, Greek for fire, and clast, Greek for broken. So literally this means broken by fire. And essentially what's happening is we have an immense ash flow that moves down the side of a volcano, very much like an avalanche. So I don't know if any of you have seen Jurassic World, but there were some scenes in Jurassic World where we had the protagonist, I think his name was Owen. He was, or I like to think of him as Chris Pratt, he was fleeing from an immense pyroclastic flow that was moving down the side of the volcano that had erupted in the film. Now, when volcanoes erupt with a pyroclastic flow, there is no escape from that flow. It's moving at hundreds of miles an hour. And the material that's in that superheated ash that's flowing is hundreds of degrees Fahrenheit. It's like putting your oven on broil. And so that essentially is flowing super fast down the hillside, and when it solidifies, that ash can carry broken pieces of rock along with it. So again, it's very much like an avalanche. Instead of snow flowing down the side of a mountain with rocks, it's volcanic ash that's flowing down the side of the mountain. And so the best example of this that we have on the slide is an igneous rock called rhyolite. Rhyolitic flows often are developed from a pyroclastic flow. And that's what we have from this image from geology.com. So we'll talk more about pyroclastic flows when I talk about, again, different types of volcanic eruptions in a later lecture. So composition is something that we've already learned about with the different types of minerals that develop out of Bowen's reaction series. So mineral composition in igneous rock is going to be either mafic or felsic. Now what I want you to keep in mind is that from that previous slide that I showed you before, we've got different proportions of silica present in our minerals and in our igneous rocks. So mafic minerals tend to have less silica content than our felsic minerals. And again, this can cause a difference in the appearance of our igneous rocks. So on this slide, I've got a lava flow, and this lava flow comes from Hawaii, and this ropey lava flow of basalt that's gradually solidifying will not only have a distinct texture, usually aphonetic, but it's also going to have a distinct mineral composition based on the magma and the lava that's developing at this point. So we've got felsic igneous rocks, and again, these contain mostly combinations of feldspar and quartz in their mineral composition. Now, felsic igneous rock, the term felsic is just referring to its mineral composition. It has nothing to do with where it formed per se. So you can have felsic igneous rocks that are intrusive, or you can have felsic igneous rocks that are extrusive. So intrusive and extrusive have to do with where and how the rock developed. Felsic, mafic, and intermediate have to do with these combinations of minerals that have solidified out of either magma or lava solution. So in this example, I've got felsic igneous rocks, we've got granite, and I also have an image of El Capitan, which is again another monument from Yosemite National Park. And we've got rhyolite, rhyolite being an extrusive felsic igneous rock, here with the rhyolite flow with a camera lens for scale. Then we have mafic igneous rocks. There are two, again, examples here. So we've got extrusive mafic igneous rocks like basalt. So basalt, again, is aphonetic in its texture, but it is extrusive and mafic. So in other words, it's got much less silica present in it. It's got more iron and magnesium, and as a result, it's a darker color. And so here's our basalt. It's got this lava flow, again, from Hawaii that's solidified out, showing how the basalt will gradually form over time. And then we have gabbro. Gabbro is an intrusive igneous rock. You can tell this because of the crystals. So it's got larger crystals here, usually phaneritic, as we can see in this image from geology.com. And this gabbro, again, is an extrusive mafic, or intrusive mafic igneous rock. So it's intrusive mafic. Mafic meaning, again, that it's got much less quartz and feldspar present than what we have in the previous set of rocks. And as an example of a location that has gabbro present, we've got sections of the Scottish Highlands in this image. Finally, we have intermediate. So recall that intermediate magmas and lavas are a mixture of both felsic and mafic minerals together. And when this happens in our rocks, they usually develop either a gray color or a blend of black and white minerals that are appearing on the surface. So for our extrusive intermediate igneous rock, we have andesite, and we've got the Andes Mountains as well. So we have andesite and we have the Andes Mountains, and then we have diorite. And with diorite, all I have in this slide is just a sample of diorite, hand sample, but we've got alternating sections of amphibole and maybe quartz or feldspar. And again, these crystals are large enough to where I can identify them with relative ease. So we've got, again, an intrusive specimen. So andesite is extrusive and diorite is intrusive, but both of these rocks are classified as intermediate because they develop combinations of felsic and mafic minerals in that magma or lava melt and solution. And so that wraps up our igneous rock lecture for this week. We're going to continue our discussion of igneous rocks and magma and lava with our next lecture, which is volcanoes. We'll learn more about the different types of volcanic eruptions and how the chemistry of the magma and lava influences how those reactions happen and how that volcanic activity can change over time and at different places on Earth's surface.